Just after we recorded this interview, we got news from White Quark that Nmygen's name is now Amaranth. So hi and welcome to another interview for the Zero to ASIC YouTube channel. And today I'm very happy to be joined with Myrtle Shah. How are you doing, Myrtle?
Hi, doing well. Very nice to be here today.
Yeah, so people probably know you from your FPGA work. So you did a lot of work on Project Trellis and NextPNR. How's that been going?
Yeah, that's right. And I'm still very much maintainer of NextPNR, continuing to look at ways of actually developing both ASIC and FPGA tooling together and maximizing the combined work on both looking into the future.
So, has there been any recent upgrade? I think you did a version release recently, didn't you, on NextPNR?
Yeah, that's right. So that had been waiting for a while for a new Yosis release, because for a long time we were on Yosis 0.9, which was too old for upstream NextPNR. But with more frequent Yosis releases, it also means we can do linked NextPNR releases. So that's an important step for getting NextPNR into the hands of distribution packages and generally making it more accessible. And hopefully, I believe there are plans for more frequent Yosis releases. So hopefully we can combine them with NextPNR releases as well on a probably not quite such a frequent, but ultimately regular schedule.
And I think I was reading you had some experimental support for partial reconfiguration. Is that what's going on with that?
That's somewhat been stalled due to other things going on, to be honest. But yeah, that's something that's definitely on my to do list, and been gradually investigating some more Xilinx support, and also working with Lofty on their project Mistral, which is Intel support for NextPNR. So the most recent change on that was adding support for the Intel's LUTRAM primitive, so that can start to work towards building more complex designs.
One of the questions we had on Twitter was, "Is NextPNR dead?" So I think we can conclusively say no.
No, 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 certainly not. In fact, just the other day I was looking at going through the next PNDAR code, looking at remembering how the placer worked in order to experiment with the same algorithms for ASICs, and now I've actually thought of a nice way of refactoring the next PNDAR placer as well, so that will be coming in the next few days.
Yeah. So you mentioned that you've been not had too much time for it. You've been working on other stuff. So maybe now's the time to talk about some of that other stuff. What have you been up to
Yeah,
recently?
that sounds good. So yeah, a project that I've been involved in, and I think Staff was here talking about a bit earlier, is uh, starting to get some tape outs up and running using Coriolis for place and route in combination with Nmygen for the SoC build and integration, and yeah, Staff's FlexLib cell library and PDKMaster framework.
And you recently you were preparing something for the eFabless Skywater Google MPW3, right?
Yeah, that's right. So there was a lot of excitement there, some quite late nights, but unfortunately, a last-minute hitch, a density failure on the FOM field oxide metal. I think that is, but I may be wrong. Anyway, we had unfortunately, yeah, last-minute failure there meant we didn't make the MPW3 tape out.
Dang. So plans for
Mm.
MPW4 then?
Yeah, that's right. So pretty much the same SoC, but with some improvements to the cell library, some small improvements, tidying up the flow a bit because we're in a bit less of a rush, and yeah, trying to increase the density, the amount of diffusion in our fill cells and in the cell library in general, so that we pass that check.
Yeah. So I think we just maybe need to go back and unpack that a little bit. So we had kind of three things there. We've got Coriolis, we've got Flexcell, and we've got Nmygen. So
Yeah, that's right.
I did talk, you're right, I spoke to staff about Flexcell. So if you're interested to find out more about that, then you can check that interview. But how would you sum that up, Myrtle?
So the important thing about Flexcell is that it's a Python-based framework for generating ASIC standard cell libraries. And just so very briefly, modern digital ASIC design, you don't place and route individual MOSFETs, for example. What you do is you combine MOSFETs into gates, things like NOR gate, NAND gate, flip-flop. And then those gates are like basically boxes that you place and route and synthesize to. And so traditionally, like And creating these cell libraries has been a bit of a black art. And while there are tools that do some of it, it's not something that's generally there's been a kind of very sort of production-ready open source flow for building a cell library across a wide range of processes. So Flexcell uses a kind of combination of different approaches in order to get relatively efficient cell libraries that can be built for all kinds of processes. So it's starting, I think, for things like Sky 130, but hopefully we can move it to smaller processes in the future.
So is that kind of the idea that it gives you a bit of freedom and flexibility from whichever PDK you're working with? You can generate your own standard cell library.
Yeah, and although we're not quite there at the moment, there's some interesting ideas, for example, in terms of generating custom-sized cells in order to get like a particular trade-off, rather than just having a fixed set of cell sizes to choose from. You could, generate them on the fly depending on the demands of your design.
Okay. And then normally, I think people who are subscribers to this channel know that the kind of the default tools that we've been using for the Google sponsored free shuttles with eFabless is OpenLane. So that's based on the DARPA funded Open Roads kind of core utilities there. But we had Jean-Paul Chaput, who's the lead architect for Coriolis, do a presentation for Open Tapeout recently. And that's an alternative RTL to GDS flow, right?
That's right. So we primarily, in this context, we're actually looking at not so much RTL to GDS, but synthesized netlist to GDS, because in both the Coriolis and the OpenLane flows, Yosis is used to get from RTL to synthesize netlist. And so for both those flows, that first step is pretty much the same.
Okay. So yeah, if you want to find out more about that, then check out Jean-Paul Chaput's talk and demonstration. And then the other part that you mentioned is using Nmygen.
Yeah, that's right. So if you're not familiar with Nmygen, it's a Python-based framework for generating hardware. It's important to note that what Nmygen isn't doing is compiling Python directly into hardware, but instead using Python to construct logic and hardware and RTL basically.
So what's the advantage then of using that?
So one of the big advantages that it gets you is better meta programming capabilities for things like doing resolving things like address buses for system on chips, that kind of integration type task. It's well suited to, and it's also because it's a much more modern design than traditional inference based RTLs. It tends to have fewer soundness issues as well. And just generally, it takes advantage of being a greenfield design to fix some of the kind of what you might call bugs in the Verilog standard around things like signedness.
Okay. So let's talk a little bit about the actual design that you are hoping to tape out for MPW3. That's an SoC, right?
Yeah, so it's just a proof of concept of how our different bits and pieces could integrate together. So it combines a Lambda SoC RISC-V core, which is a RISC-V core written in Nmygen. Sorry, go back. A Minerva RISC-V core, which is a RISC-V core written in Nmygen, combined with Lambda SoC, which is a system-on-chip framework in Nmygen, and so that's kind of the core. And then we have a small amount of built-in RAM, because we don't have any SRAM primitives yet. That's actually just using kind of basically just synthesized to flip-flops using Yosis. Then on the peripheral side, we have Spy Flash to boot from, which is using Claire Wolf's Verilog core from PicoSoC wrapped in Nmygen. HyperRAM for RAM extension, which uses the port of the light Hyperbus core to Nmygen, and then just the bare minimum peripherals just to do Hello World, so GPIO and UART.
And is this going to be Linux capable, or what's the?
No, this is going to be more just for running simple test programs. A Linux capable SoC is probably more of an MPW3 target once we have
Okay.
Vexris 5 up and running, a better cell library, and the ability to do more on-chip RAM for things like cache.
Okay. Okay, so we've got up on the screen the kind of the top level Python that is written in Nmygen. I was wondering if you could talk through it for us.
Yeah, sure. So the kind of heart, as I said, is the Minerva RISC-V CPU, and as with many modern CPU cores, the instruction bus and the data bus coming out of the core are separate. In this case, we have an arbiter. That's something that enables a single bus to be shared between multiple bus controllers. So that shares the main system bus between the instruction and data bus. And then we have a decoder which enables multiple peripherals to be connected to the same bus, each occupying a different region of addresses. So the CPU is in orange, and then the arbiter and decoder in the coder above in yellow and blue. The next peripheral below the CPU is the SPI flash interface. That's a memory mapped SPI flash interface. So a read from that bus directly translates into a read from SPI flash. And there's also a small control bus that enables things like quad SPI mode. So that adds 2 buses to the decoder. Following on from the SPI flash, we have the built-in SRAM. And then after that, we have the HyperRAM interface, which is some extra, which is a form of external RAM that can be it's essentially a hybrid between SRAM and DRAM, but that's connected there to the HyperRAM I/O and to the decoder. After that, we have an async serial peripheral, a UART, and then a timer, and then we connect both the UART and the timer to an interrupt controller that enables them to interrupt the CPU as needed. And then finally, we've got a small GPIO peripheral.
It looks very neat when you see it written out like that.
Yeah, I mean, obviously, there's going to be stuff backing up behind this. So this is like the top level integration, but so it's one of these things where the top level is neat, but obviously there's always going to be a degree of magic underneath making it work like this.
So, how much of the peripherals and things like that are also written in Nmygen, and how much are in some other HDL and then kind of wrapped up to make it work in this context?
In this system on chip, the only peripheral which we've chosen to use in Verilog is the SPI memory interface.
And that's the one from Pico OV32, PicoSoc.
Yeah, PicoSoc, that's right. Just because it's a core that I've used much in the past, and it's sort of tried and tested for me.
Okay.
The HyperRAM core was originally written in old Nmygen from Litex, but I decided, although Nmygen has some compatibility for that, I decided it was not a complex core, and it was easier to actually rewrite it in Nmygen, or not exactly rewrite it, but just find and replace as needed to upgrade it to Nmygen, rather than try and use the compatibility layer.
And I think actually we've got a name change coming soon with Nmygen, don't we?
I believe that's right. Yes, I believe
Yeah.
White Quark has certainly hinted
Yeah.
at that several
Okay.
times.
Yeah. We'll keep you posted, but it's currently still Nmygen.
Yeah, we'll have to dub the audio if it's changed.
All right.
Yeah.
And then I'm just now scrolling down a little bit further in the actual source code.
Mm.
So maybe you can talk a little bit about how the memory map is created, because that kind of looks like that's quite a helpful thing that gets mostly done automatically.
Can you just tell me actually exactly which bit you're
I'm on
looking
line
at?
161.
That instantiates the SoC we described earlier with some configuration settings. So actually, at the moment, these addresses are picked manually, mainly because you want some consistency in your addressing. So it's kind of easier just to pick them manually once and have some software that's going to be potentially changing them several times.
Okay. And then with that, when you come to actually write firmware for this, would this then generate the linker script and stuff like that?
Yeah, that's right. That's part of Lambda SOC. It generates header files and linker scripts for the peripherals and for the memory map.
Okay. So yeah, so what kind of stuff do you get inside Lambda SOC? I think that might be interesting to know.
So Lambda SOC provides at the moment a Wishbone bus interface, decoders for the Wishbone bus, and integration with the Minerva CPU core, and the ability to build a simple kind of bootstrap BIOS for that.
Okay. And one other question we got from Twitter was from
Yeah.
Ippolito Guzman. Hi, Ippolito.
Mm.
Talking about how did we implement SRAM. So we've already heard that you actually didn't do that. You didn't use Open RAM. You synthesized some memory, just some DFF RAM with Yosis.
Yeah,
Are
that's
there
right.
are there plans in the future to put more memory on the core itself?
Yeah, so as part of the cell library project, staff wants to work on FlexRAM, his own memory compiler, and once that's up and running, we'll do a test chip with some memory that's been built using that.
Okay. So is the idea there that you want to get memory as close as possible to the core? Like why not just use the HyperRAM?
So the HyperRAM is always going to have higher latency because you've got to go through an external interface. Particularly in the case of HyperRAM, it's a fairly high latency interface. And so even if HyperRAM is used, say, for your main memory, then you're still always going to want things like caches and register files to use on-chip SRAM.
Okay. So what kind of amount of RAM are you aiming for then, I guess?
So on the kind of test chip one, I think we had 512 bytes, but I think with kind of a really good memory compiler and a denser cell library, I think maybe up to sort of on the order of 8 kilobytes should be doable.
And would that still be sticking to 130 nanometers, or would you need to go to a smaller?
Yeah, so that's sticking to 130 nanometers. We could potentially do a lot more on a smaller processor with more area available.
Okay. Cool. Okay. So any other stuff that you're working on at the moment?
Um, Nothing of probably of interest to this, I don't think. Yeah, no.
I mean, I think probably adding new FPGA support to next PNR, taping things out, doing your first ASICs, that's probably quite a lot on the plate already, isn't it?
Yeah, I mean, there's some bits and pieces like some Yosis HQ and stuff, but it's
Yeah.
not exactly stuff of particular public interest. So yeah.
I guess one other thing that I'm interested to know about are what's it like working with ASICs after, your intimate knowledge of how FPGAs work?
I guess one of the strangest things is how much more real everything feels. So I was working on a toy ASIC placer just recently, more as a learning exercise than with any particular goals in mind. Essentially, a port of the next PNR placer to ASIC, and when you're working in the next PNR placer, everything inside FPGAs is kind of done on arbitrary grid units. But then suddenly you port it to ASICs, and your wire length is reporting as 8 meters, and it's actually like a concrete unit of measurement rather than just some arbitrary number. So it kind of changes how everything feels a bit.
8 meters, as in like 8 real meters of wires.
Yeah, that's and obviously there's going to be some physical length inside an FPGA, but you never
Yeah,
really know it because those details are abstracted away. Whereas
yeah,
in an ASIC, it just really is a real length that's sort of just there.
yeah. When I do synthesis, with for the ASIC flow, and I might see, okay, I've got 30,000 wires, but I never thought how many meters it would be if I added them all up.
Mm, yeah. So this is actually an estimate of wire length after placement. This is half perimeter wire length. So once it's actually been routed using, say, Steiner trees or whatever, the actual wire length will be a bit higher than that as well.
Okay. So, any other similarities or differences between the two?
I mean, I think in many ways, like between standard cell ASICs and FPGAs, there are a good chunk of similarities, particularly on the placement side. On the routing side, ASIC routing tends to be split up between two steps: global routing, which is kind of finding a rough route, and that uses sort of abstract routing graph, a bit like you might for an FPGA. Detail routing is where ASIC stuff becomes very different from an FPGA because you're physically playing with bits of metal in whatever shape you like, rather than just configurable switches.
Yeah. And I suppose, because something I found out quite recently was that there's an option, I don't think it's that popular anymore, but where you have the bottom layers defining a matrix of MOSFETs, and then you just customize it with the metal layers, connecting it up.
Yeah, so there've been lots of attempts at things like this. Sometimes they even go more than that, and they define almost all of the metal as well, and it's just actually just a via layer that you configure. And when you're configuring a via layer, that's pretty much identical to configuring switches inside an FPGA.
Yeah. So then there is this kind of middle land in between the two there.
Yeah, definitely.
Okay. Great. Okay. Anything else you want to mention?
I think that's probably it. So yeah, excellent.
Great. Okay. Thanks very much for your time, Myrtle, and I'll see you about.